I've been using Linux full-time for about 10 years now. I work at Bluehost, maintaining a number of systems and whatnot for them internally. And I am also somewhat passionate about networks, and hence IPv6. Before we get started, real important question. Have people dug into the pizza yet? Because I don't want to hold people up if they want to grab pizza and the smell is driving them nuts. This is an intro to IPv6. That P should have been capitalized. So this is a modification of a presentation I've done a few times in the past for Plug at the OpenWest conference. Actually, back then it was the Utah Open Source Conference. Several other times in the past I've given a version of this presentation to various groups, and it's something that I like to come back to every once in a while just to give additional people some more background into it, and also to remind people of how this is the future. We need to be working on this, or we're going to be in a really bad state in the not too distant future. So here's some of the things we'll cover. I'm not going to spend any time on that right now. So to start off with, this is something new and different. I want to take a little bit of a walk through history on a little bit of background for IPv6. And let's start off with going back to 1993. I looked so innocent. I was so naive. I spent way too much time watching Star Trek: The Next Generation as new episodes were airing. Windows 3.1 was out. Let's see. I think the family computer at the time was a Compaq 486. So yeah, spent way too much time there. Cowboys won the Super Bowl that year. I'm from Texas, so got to put a plug there, even though I'm not exactly the biggest Cowboys fan. But in terms of our conversation, RFC 1550 was issued by the IETF asking for the next generation IP protocol. IPv4 had been around for years at this point, and it was really the idea of the internet and a global network for people to connect to was really starting to take off, and they realized we've got some issues, and so they put out a request for proposals for whatever the next generation IP or internet protocol is going to be. Over the next few years, a few proposals were made. There's one of them that took the lead, and we're going to jump forward now to 1998. In 98, the Zarya, the first International Space Station module, launched. I was still using Windows. I hadn't tried Corel Linux yet, so I still didn't know anything better. I definitely wasn't much wiser. These two films came out in the summer. One of them was, even though they had a similar theme, one of them was very distinctly a Michael Bay film. But coming back to our conversation, RFC 2460 was released, or finalized IP or Internet Protocol version 6. And so we can see, IPv6 is not exactly something new. It was ratified in December of 1998. If it was 1 month earlier, it would be old enough to vote in this November's elections. It would probably be just as disappointed in the choice of candidates. Some other things. So I have spent a lot of time with these. They are awesome little devices. But in December 2002, the WRT54G comes out for the first time. It and a lot of other devices that sprung up around this time made, as well as broadband, brought NAT into the common person's network. And it made us forget about things like IPv4 exhaustion. But then there's some additional dates here. I don't have pictures for these because there's not really anything ceremonious about them. But does anyone know what happened on January 31st, 2011? So that was the day that ICANN, the organization that handles allocations of IP addresses and ultimately the domain name system, they issued their last /8 address ranges in their inventory to the regional registries, regional internet registries. They still had some IP addresses available to allocate, IPv4 addresses to allocate to people, but they had gotten rid of their biggest blocks. So there was, from ICANN, they didn't have any more large v4 address spaces to give out. On May 20th, 2014, they did give out the last of their addresses. At that point, if any of the regional registries needed more address space, tough luck. They had to either reclaim it from previous allocations or, deal with it. And then the big one, at least in terms of us here in North America, is on September 24th, 2015, Aaron, I can't remember what the acronym stands for. They're the regional registry that handles IP allocations in North America, specifically the US and Canada.
American Registry for Internet Numbers.
There you go, American Registry for Internet Numbers. On September 24th of last year, they gave out their last IPv4 allocations. So if you're creating a network where you need to get get public IPv4 space, you're pretty limited on your options now. You can either grab it from your ISP, which ISPs do still have decent stocks of IPv4 addresses, but that's going to be going away, and it's getting harder and harder to justify allocations. Or you have to do or find someone else who has v4 space that they're not using and get them to transfer it to you. Now, it's a scarce resource. No one is doing that for free. These days, if you want to go looking and go to the quote-unquote transfer market, it's going to cost you anywhere between about $8 and $15 per IP address. So just the smallest /24 that you can get is going to cost you about $6,000. So it's not something that's cheap anymore. So v4, we've known for a long time that its lifespan was limited. We have delayed migrations to it for a long time, but we've got to get moving on to the next thing. I'd be a little surprised if many of you have to worry about this directly from a work perspective, but if the company you're working for has much of an internet presence, if you haven't already started your conversations about how you're going to implement IPv6, you're already behind. I wish I had some coworkers here because I really wish I could get that point across. I guess I have one coworker here, but not in the group that I deal with. So it's really important that the v6 transition has at least been talked about and started. Otherwise, you're already behind. Luckily, it's already in a lot of places. So anyways, a few questions. I don't know how many, it didn't sound like many of you in here have much of a network background. But here's a few trivia questions that we'll be answering throughout the talk. I'm not going to ask them now. We got other stuff to get through. So IPv6, what are the basics of it? Well, it's the next generation of the Internet Protocol. In terms of the OSI network stack, if it's right where IPv4 was before, like I was talking about, it's been around since the 90s. And this is the big problem on why it took so long for even really IPv6 to really start getting any traction, is it's not natively compatible with v4. So if you're on the v4 internet, you can't start talking to the v6 internet without having a v6 connection, at least natively. If you're on the v6 network, you can't natively talk to the v4 network, which we have a lot of stuff on the v4 network. There are various methods to make that transition easier. The big thing that really people should be talking about these days is having a native dual stack implementation in their networks, and having v4 and v6 addresses on your hosts and your networks. There are things you can do to handle a transition, to translate between the two addresses. Those get into some pretty advanced topics that even I get confused about, so I'm not going to go into those. But the nice thing is with IPv6 is that the layers, so even though we're incompatible, the layers above and below v6 generally have stayed the same. We still have TCP and UDP on top. We still use a variety of underneath networks, such as Ethernet, Wi-Fi, all the other things that we transport IP over. Those still all work. I guess DOCSIS, the cable modem standard, did have to have an update so that it could handle IPv6. If you have cable service at home, if you have a DOCSIS 2 modem, you're not going to be able to get IPv6 service. You have to have a DOCSIS 3. So, but anyways, here's some quick little diagrams of the OSI model. I don't know how much you guys have experience with it, but at the bottom we have our physical layer, which is our actual network connections, the physical connections. So the example I give is 1000 base T, which is standard wired gigabit Ethernet. Wi-Fi is another example. Above that you have your data link layer with Ethernet, and then here's the network layer with IPv4. And then above it we have our transport protocols such as TCP, UDP, SCTP, and then everything else above. We're not going to care about that. The way that it changes with IPv6 is we just change this in here. There's one more thing I probably should have added in here is ICMP, the Internet Control Message Protocol. It went through some major revisions as well with IPv6. So usually when talking in terms of ICMP, if you just say ICMP, that means the v4 version. ICMP 6 is the v6 version. Some things such as there's not ARPs in v6. The v6 terms, it's called NDP, or the Neighbor Discovery Protocol. A few other things like that have changed for v6. So why did we need a new version of IP? Well, the big thing is that we were running out of address spaces, and NAT is not a solution. NAT isn't even a security answer, in my opinion. A lot of people think of NAT as, it prevents people from hacking into my network. NAT itself doesn't do that. The fact that you have a stateful firewall that's dynamically doing those NAT table updates is what gives you that security. And if you have a stateful firewall doing that, you've already got a stateful firewall that you could use for regular routed traffic. And it's actually a little simpler. So NAT's not a security solution even. We had no practical way of extending v4, and it's a chance to make some improvements on lessons learned. One example, I don't have it in the slides, but when it comes to, say for example, switching equipment, you want to be able to determine what your destination is as soon as possible. Well, with IPv4, it's the source address is first in the packet, and then the destination address comes after it. So you have to wait for a small period of time to find out what your destination for the packet is. IPv6 reverses that. The destination address is first, so that the equipment can quicker decide what the destination of the packet is. But there were some things that maybe didn't get better. And we'll talk about one of those a little later. Comparison with v4, much bigger address pool. If you've ever used an application that uses broadcast traffic, that doesn't exist in v6. Everything is multicast. So if you have applications that rely on a one-to-many transport mechanism, learn how to do a multicast configuration. It's not that hard. Stateless autoconfiguration is one thing that's kind of cool. They kind of borrowed from IPX and made it so that devices can configure their network addresses automatically. They don't have to have something telling them what their address is or have a static address configuration. Here's the simplified headers. That was one example with the change of the ordering of addresses. One nice thing is that even though the address space is much bigger with v6, the number of routes in the global route table are actually a lot smaller. Reason being is that because there's so many more addresses, we can be somewhat wasteful in our IP allocations to make things make sense. Whereas before, with IPv4, we had to scrounge for every little bit of address space we could, and a few other minor changes. So where is v6 used? Well, there are a lot of places that currently use it. Pretty much every major website is going to have support for it. Oh yeah, so my last version of the slide deck was done just after kernel.org got hacked. So that's why there's the comment about when kernel.org is up. So this has been a few years. So for example, IPv6.google.com, that's a DNS name that only resolves v6 addresses. So you can use it to verify that your IPv6 is working. Google does actually publish IPv6 addresses for just google.com and www.google.com. And so if you have a working v6 stack, there's actually a decent chance that whenever you talk to Google, you're talking to them over IPv6. And I don't remember the latest stats, but last I knew, Google was reporting about 10% of their global traffic was coming across the v6 network. Every major OS has support for IPv6 natively, even Windows 2000. I experimented with it in Windows 2000. It didn't work as well, but it does now. So when it comes to everyday users and home use, what ISPs support it? Well, Comcast and Google Fiber have it working just out of the box. If you have a router that supports, actually with Google Fiber, you're most likely going to be using their router, and it's just going to do IPv6. You won't even notice it. Comcast, if you use their router or you use your own router that has v6 support, it's just going to work. These other places, it supposedly works. I haven't tried them myself yet, but Comcast and Google Fiber, I have done myself, and we're actually going to be seeing it on Comcast in a few. So what all does IPv6 mean for people? Well, for end users, hopefully it doesn't mean a thing. Like I said, if you have one of those providers and are using their equipment, you have v6 probably working already. And if you're talking to websites like Google or Facebook or Microsoft services, you're probably talking to them over the v6 network already, and probably didn't know it. To system administrators, there's an additional set of IP addresses that you have to worry about. On Linux, there is a separate firewall. So your standard IP tables commands don't do anything to filter IPv6 traffic. There's IP6 tables that does that. Or if you want to be ambitious and learn NF tables, which is the thing that's supposed to replace the other two, that handles both of them as well. When it comes to developers, if you're doing low-level socket code, you would change AF inet to AF inet 6. And you'll probably have to do a few changes around how you do name lookup. So when you resolve an address to a name to an IP address, you probably will need to change which functions you use to do that resolution to get these addresses. But if you're using higher level frameworks, it should just handle it for you transparently. And I have a Python example in a little bit that shows just how simple and easy it is. To network administrators, well, I'm not a NetOp. I kind of halfway pretend to be one. The v6 should make some things like address allocation a lot simpler. In cases where you're running networks in multiple areas or just have multiple networks even within an office or something like that, having the larger address space and being able to just say, I'm going to allocate a large chunk to this network and then splitting it off from that can reduce the amount of routing that happens, or the route or entries in your route tables, etc. So, but that one gets much more complex, though once you start doing it, it's not that far off from the v4 space was. So let's start talking some of the technical aspects of IPv6. There are 128 bits to the address space, which is a whole lot of addresses. In fact, that's what it comes out to be. That's a really big number. The way that I thought about it is, right now, we've got, let's just say, just shy of 8 billion people on the Earth right now. So that's 2 to the 33rd. And we have 2 to the 128th addresses. So the standard, I should have put that as prefix. The smallest network size is a /64, 64 bits.
Is IPv4 only 4 billion?
Yes, so I should say IPv4 is only 32 bits, so 4 billion. So we don't even have enough addresses in v4 for everyone on the planet. In fact, we barely have enough for 1 for every 2. But if we do a little bit of math here with, 2 to the 128 minus 2 to the 33rd, that comes out to what? To 63 or 65 bits? Yeah, 65 bits. So to put it another way, we could give, or there are enough addresses in IPv6 that we could give every person on the planet half of the address space of v4 worth of /64 prefixes. So we could give every person 2 billion /64 prefixes. So the /64 prefix is kind of equivalent to a /24 in IPv4 world, if that makes sense to you. That's an insane number of addresses. So the big part with, or one of the big headaches with dealing with that many addresses is what notation do you use to describe these? It's not like we can use what IPv4 did and just go with the the dotted quad notation, because that doesn't represent enough addresses. So this is what IPv6 addresses look like. We actually represent them in hex numbers, and we split them into 16-bit groups. So that's 8 16-bit individual groups. So this is an example. This would be a link local address to a MAC address. I can't remember where that MAC address came from. I generated that from one of my systems a while ago, but either way, those are a little long and hard to remember. Granted, DNS should solve this for you, but how many times have you guys just used IPv4 addresses directly? Still have a use for just typing out an address. So there's a couple shortcuts we can use to shorten it. First off, any leading zeros in an individual group can be omitted. So for example, in here, these cases where we just had a bunch of zeros, or on the end here where we had 0001, we can just take out those zeros, because we can then fill them back in later. The second rule is that successive groups of zeros can be consolidated to just colon. So for example, right here, we had 3 zeros in a row right here. They were just dropped to just some colons. But this particular shortening can only be used once in an address. So if you had 2 spots where you had groups of zeros, you could only do it for one of them. Specifically, I think you have to do it for the first one.
First being on the left?
Yes, the left-hand side one. So having a colon inside of an address space separator can cause some problems because we use colons for other things, especially, say, for example, URLs. If you want to use a v6 address inside of a HTTP URL, you wrap it in brackets, square brackets like that. There are other places where you'll need to somehow differentiate a IPv6 address from surrounding bits of information. Using square brackets is frequently a way to do that. So let's see. Prefixes are very much like subnets in IPv4. It's the exact same concept, they just changed the name. I mentioned that /64 is the basic size. /48 and 56 are common allocations for end user networks. So with Google Fiber that I have at home, they actually allocate to me a /60. So I've got 8 networks that I could then use internally, 8 /64s that I could use internally for my own purposes. Right now, all of our global unicast addresses fit in just a small subset of our address range. In fact, we're only using 1/8 of the address range for our entire internet right now. Now, there is the exception for a few things, which is where some of our special addresses come from. :/0 is kind of the equivalent of just 0.0.0.0 in IPv4. We only use one address for localhost this time instead of a whole Class A network like we did with v4. Here's where we have some of our special cases. FE80, if you see an address like that, that is a link local network. You can only talk to devices on which you share a physical media using those addresses. FC00/7 is the equivalent of RFC 1918 space in v6. There are a number of RFCs around using that address space. In one of them, it actually gives you an algorithm you should use to generate what network you should use inside of there. That's kind of fun to go through. I actually used it at a previous job to generate a v6 network range for us to use internally on the company network. And then it never got implemented. 2001 DB8. This is reserved for documentation purposes. How many of you knew that there was an IPv4 address space reserved for documentation purposes? One. And it's probably because I told him.
Could be.
So if you're writing documentation and need to use IPv4 addresses in it, 192.0.2.0 is reserved for documentation purposes. 2001 DB8 is the v6 equivalent of it. When it comes to configuring IPv6, on a Linux system, you're really going to want to use the IProute2 commands. I think ifconfig has really basic support for it, but you're going to be much better off using IProute2, or in the examples here, just the IP command. With to specifically see your IPv6 addresses, you can add just a -6 option into your commands, and it will only show you your options related to v6. Adding an IPv6 address to an interface is the exact same as it would be for IPv4, except you're just changing which address you define. Adding a route is the exact same as you would for v4, except just using different addresses. In this case, ::/0. We said on the previous slide that's the default. So this command is saying, send all your default traffic to this other link local address. So it's very much like you would configure them for v4 using the IP commands. Manually configuring things is less than fun, and so we do have some automatic tools to help us. The first one is Stateless Address Autoconfiguration, or SLAC. This is a way for a device to automatically configure its IPv6 addresses. The way it works is, first a individual device or node on the network is going to generate a modified EUI64 address, and that will give it 64 bits or a 64-bit address based on its MAC address. I'm not going to go through the exact steps that it happens right now, but for example, this MAC address would end up turning into that lower half of an IPv6 address. So we only have 4 groups of numbers, so that's only half of our address. The other part of stateless auto-configuration is router advertisements. So on some kind of periodic interval, routers on networks will send out a IPv6 multicast address saying, hey, I know how to get to these other networks, basically a default route type thing. I mean, I'm not quite saying it exactly right there, but close enough for our discussion. So devices that are on the individual network will see these router advertisements. They'll see what address range it's advertising and use that to populate the upper 64 bits of their address. And so by combining the address they generated for themselves plus the address they saw on the network, they now have a full 128-bit address and a default route or route to other networks, which they can then use to talk on the internet. So that's just one thing, but all that does is give us an address. There are other things that we frequently need to configure network-related on hosts, such as what your name servers are. In the case of, say for example, if you want to do network booting, you need to know what your the next server, the TFTP server is. You need to know what file name off it the Pixie client needs to download, etc. And the stateless autoconfig by itself can't necessarily provide those bits of information. And so now we have DHCP v6. It shares some things with v4, but it's also a very different beast than DHCP v4. High level does the same thing. Clients send out a multicast asking for an address. A DHCP v6 server or a relay will pass it on to a server. We'll get the message, assign an address potentially, and return that to the client, who will then configure things. This is one way where it kind of feels like IPv6 regressed. With DHCP for IPv4, the thing that identified a client was just simply its MAC address. With v6, that's not necessarily the case anymore, or it's not just the MAC address. There's 3 ways that are defined to come up with a DHCP unique ID. The first one is link layer address plus timestamp. So basically, you take your MAC address and you add a timestamp to it. The problem here is that, say, for example, your system gets reinstalled. At least in terms of talking lots of servers, if you go through and reprovision one of your servers, you've then lost that timestamp, and you're going to get a completely different DHCP allocation. But it is still a commonly used way. It's probably the most common when it comes to DHCP for DHCP v6. Outside of maybe enterprise networks. Then there's the DUID-EN. This one is just an enterprise to assign ID. Enterprise quote unquote. This one just has a ID and then a random string. Google Fiber actually uses this one on their network boxes. Back when I was doing some exploring on how they actually ran their networks, I found they were using their unique, actually it was an identifier for a company they acquired, I believe. And then they were using a number unique to the box that was not the MAC address. I don't want to give away too many details because I don't want Google Fiber coming after me. But they used the DUID-EN. Then there is also just the link layer address, but this one, not many bits of software have support for it. At least last I went looking, there weren't really any clients or servers that had support for just the link layer address in DHCP v6. Oh, and what's even better is the client is free to choose which one they want to use. So the server doesn't even know which method the client is going to try. So when it comes to enterprise networks, you would have full control over that, but unfortunately, in my opinion, software still has a little ways to go to catch up. There's also the combination of stateless autoconfiguration and DHCP v6. Stateless autoconfig has a couple flags that it can use to signify to the clients that additional work needs to be done. Microsoft uses these to determine what to do for the v6 auto configuration. By default, it doesn't use DHCP v6 unless one of these flags is set, in which case it will then go ahead and use DHCP v6 as well, or in place of. So yeah, the other thing about DHCP v6, I don't recall if I had it on the slide here. I didn't. So one really neat thing that DHCP v6 does allow for is what's called prefix delegation. And where this is useful is in the case of edge network devices. So say, for example, your company router talking to the internet. It's going to use DHCP v6 to get an address from your ISP's network, but it also needs IP allocations to use on its internal networks so that v6 addresses are routed properly. And so DHCP v6 can actually delegate some network ranges to the client, and then route tables will get updated properly, and routing just happens. So that's one cool thing about DHCP v6. When it comes to testing your network connectivity, ping, just like with v4, is going to be a go-to command. In this case, ping 6 is what you'll need to use because ping uses an ICMP protocol messages. And like I said, ICMP went through some major revisions, so there's a different version of ping for this. If you're pinging link local addresses, you do need to specify which interface to use. Systems frequently have more than one interface, so if you're just using link local, you have to give it an additional bit of information so it can know which interface to use. Traceroute 6 is the v6 version of Traceroute. My personal favorite is if you go to www.com.net, if you see a dancing turtle that's not fuzzy, then you're talking on the v6 internet. You're talking publicly on the v6 internet. All right, so I mentioned a few places or a few ISPs that already have native support for IPv6. Maybe you don't have one of those providers, or your provider's just being stupid for some reason. At a previous job, I was negotiating new internet contracts, and I actually had a sales guy tell me no one's using v6. This was like 2 years ago. Aaron had run out. So anyways, if you're unable to get native v6 addresses from your ISP, there is an option that you have with the Hurricane Electric Tunnel Broker. This is a service that I currently use with some of the networks that I manage. It's really simple to set up. If you just go to www.tunnelbroker.net and follow the instructions, it's pretty easy to get things going. A couple caveats are is you do need to do it on the device that's on the edge of your network. So you can't run it on something that's behind the NAT, behind a NAT. You do have to sign up, give them your email address and whatnot, but they're really good about that. I don't think I've ever gotten a bit of, well, I guess I got a few network updates from them, but I never got anything from them trying to sell me services. There's the steps you could go through. In the past, I have actually gone through and done this during the presentation, but hopefully you're using an ISP these days that just has v6 addresses, so you don't have to worry about it, and which now gets us to part of the demo part of the presentation. And to start off with, I just barely hooked a brand new or a recently just flashed router with OpenWRT up to a Comcast line. Didn't do any bit of configuration on it, and v6 is already working. So we'll show that, so some command line tools, and then just a simple program. Oh, actually, I wanted to leave that up, and we'll just come over here. So in the terminal here, this is my OpenWRT box that I mentioned I just barely set up. Actually, let's come over here to this. We can make that a little bigger to make it easier to see. So I'll log into the OpenWRT interface. And if we scroll down, you can see just out of the box, I got my IPv4 addressing, and then I also got IPv6 addresses. And you can see here, this is the address that the router got through DHCP. This is the gateway that it has. One thing to notice here is that gateways are usually configured by the link local address of that device, not the globally routed address of the device. I guess this is one thing that's a little bit different compared to how a lot of people are. v6, you're going to have multiple addresses on a particular interface. So you have to be aware that one of them is link local, others are globally routable. There's also dynamic ones, etc. So anyways, you can see that you got 2 DNS servers from DHCP as well, and it's been connected for 2 hours. The other thing that we should be able to see, oh, I guess I don't have, so I only have one device on the other side and it's not using DHCP. So there's no DHCP stuff going here. If we come to the command line now, I did install the IP route commands on this box. So if I look at my IPv6 addresses, so ETH1 is my public interface, and you can see there's that giant address. And then on the private side, the box automatically configured a v6 address itself. And this was assigned to my router from Comcast using DHCP v6. And so this is now also broadcasting the router advertisements onto my network. And it's also doing DHCP v6 onto the network. Though, like I said, I don't have any DHCP v6 clients on it right now. So it's really easy. It just works. With, at least if your ISP supports it. Yes?
So let me clarify, so if you plug a device in and it gets an IPv6, is it from a DHCP server on your OpenWRT router, or is it coming from Comcast? Or is
It would be from the router, from my router, not from Comcast.
Okay, so it's kind of like IPv4.
Yeah, so let me actually come over here. So this is the box I have plugged into it. And if I look for IPv6 addresses here, so ETH1 is the device or the network interface that's plugged into the router. It got this 2601 address. This it got through router advertisements from my router. The DHCP, if I were to run a v6 DHCP client here, that would only make it to my router. It wouldn't make it to the public internet. So that still gives you the control over who gets assigned what. Usually on a home network, you probably wouldn't even worry about assigning it and just let them auto-configure. The other thing that you could do to be able to talk to devices on your own private network easily without having to configure DNS names is MDNS, multicast DNS, or DNS service discovery, two similar things but different implementations. On Linux, Avahi is the daemon that does it. It can do just name lookups. If your system is configured for it, it can do v6 lookups of boxes across the network, assuming everyone's running the Avahi daemon. So one thing to look at here, so we see that my box here has an IPv6 address. If I look at my route table, you can see I have my this is the prefix that my router has, and so that's what the link local or the local subnet is. And then here's my default via this link local address. So let's see, that ends in 6E30. If I come back over to my router and look at its internal interface, right here, this one ends in 6E30. So my one node is configured to send its default route to the link local address of my router. So yeah, there's just how simple it works with Comcast and some command line tools. Let's now look at what it takes from a programming standpoint. And let's see. So I have an example of a Python echo server. Oh, I don't have syntax highlighting. Let's see. Will it work if I use Vim? Yeah, sorry, I don't have syntax highlighting. So this is just a really simple echo server in Python. It does the basic things like creates a socket, listens for a client to connect on it, accepts the connection, goes into a loop of reading and writing back what it receives, and then exits. Pretty simple. We can test that this works by running it. And then, let's see, let's clear this. I can telnet to localhost on 9998. You can see it successfully echoes back. We can see that it received it. We'll go ahead and quit. So nothing too special there. Now let's look at a v6 version of it. So with this case, I changed which host, or the address that I'm listening on. Instead of listening on 4 zeros, I just have : : here, when I create the socket, I specify my address family as inet6. And let's see, there was one other line that was different. What was it? Oh, when printing out the connection, the address is in a slightly different format, I think. So let's go and exit out. And let's diff these two files. So there's not much change there that I had to make in Python to be able to listen, or to be able to make this IPv6 compliant. And now when I telnet to localhost, you can see it tried : : 1 again. And you can see in the server, it received a connection from : : 1. And actually, if we come back over here, oh, this might break my, yeah. I do have a bug in my code here for some reason. Hopefully that exits. There we go. So now if I check netstat, you can see that the individual program is, the protocol that it's listening on is TCP/6, which is just the v6 version of TCP. All right, so that's it for, oh, because I closed this, it went all the way down, or all the way back to the beginning for me. And so that brings us to any questions and the conclusion. Are there any questions? Or did I just sufficiently blow everyone's mind?
So if you're a system administrator, like in an enterprise, what all do you have to do? Do you need to set up a DHCP for IPv6, or can you just let them all go wild, or what steps you need to take as a sysadmin?
So the question is, if you're a system administrator running your own network, do you need to configure a DHCP v6 server for your clients, or just let them go for it? It depends on your needs. If you're not doing much if you don't care about what addresses clients get, then I would probably just use stateless autoconfiguration and router advertisements. There actually is a way to get DNS servers propagated through stateless autoconfig. There is an extension for that, so you can still distribute that information, but you're not going to be able, if you use DHCP v4 to distribute other things such as like NTP servers or PXE information and want the equivalent in the v6 space, you'll need to configure your DHCP v6 server then. There are a number of DHCP v6 servers out there. ISC DHCP server supports DHCP v6, supports it pretty well. The one caveat is that you can't use an individual running instance of ISC DHCPD that does both 4 and 6. So you have to have two separate running processes for each version of DHCP. They can still run on the same box because they use different ports, but you can't have just one running for both of them. So you'll have two separate config files, two separate PIDs. Any other questions? Yes, Doran.
Okay, so if you have a client system that receives, it gets both IPv6 and IPv4 addresses from its router,
Mm-hmm.
and then it does it wants to do a DNS lookup at google.com.
Mm-hmm.
Is it going to get both addresses, both the IPv6 and IPv4 addresses back in response to its request?
So the question is, if a system is configured with both v4 and v6 and it goes to do a name lookup for, say, google.com, is it going to get the v4 or the v6 address back? It depends. If you're just like from a client application specifying a name, it's going to depend on how your DNS resolver libraries are configured. So on Linux, how glibc is configured to do name resolution. Most distros these days, I believe their default is they will do a lookup for both quad A and A records. And if there's a quad A, they'll return that first and let the client try it. And then also, if that doesn't work, then the client can try just the A record. But if you're needing to check your name resolution, like for example from the host command, if you specify -T and then 4 A's, 4 capital A's, that will specifically look for an IPv6 address. So v6 addresses are stored in a separate record type in DNS than they are for IPv4 addresses. And it's called a quad A record. Reason being is that a IPv4 address is 4 times the size of an IPv6 address is 4 times the size of a IPv4 address. And so we have 4 A's for it. Any other questions? Yes.
So I've heard that Android doesn't plan to support DHCP version 6 and they only do Slack. Is there a clean way of dealing with that? Your organization uses DHCP version
So the question is, Android is not going to be supporting DHCP v6, so how to handle things with Slack. So far, I haven't had any issue with it. I have an Android device myself, and I've checked on multiple networks, and it does just work. So
Can you do DHCP v6 and Slack on the same network at the same time?
So the question is, can you do DHCP v6 and Slack at the same time? Yes, you can. And you can actually configure things to specify that the address allocation is handled by Slack. DHCP v6 only provides additional bits of information. So that's stateless DHCP. There's also stateful DHCP v6 mode, in which case the client should not configure its interfaces based off the Slack address and should only use the addresses returned by DHCP v6. So as far as Android, I haven't actually looked into whether or not they're supporting DHCP v6 or intend to. Considering that the other things that DHCP v6 does don't necessarily apply to Android devices, like Pixie or specifying other kind of enterprise-y type things, I don't personally see it being an issue. There potentially is the problem of if you're through Slack and the DNS advertisements that go with it, your Android client isn't configured with v6 DNS servers, that it has to fall back to v4 for DNS resolution. But that's actually been the case for most clients out there anyways. They'll actually use v4 to talk to the DNS servers to do name resolution, and then just v6 for the actual client connection. That is slowly changing. Systems can do lookups to the DNS system over just native v6 as well, but you have to have it configured as such. Any other questions? All right. Well, thanks for coming. I think that went just right at an hour. So, thanks.